Let's start with what we know, and what we've decided about the geometric series is really important. So in a geometric series, it looks like a plus ar plus ar squared plus ar cubed, right? You keep getting one extra factor of r all the way up to ar to the n. And what we know is that that infinite sum is equal to a over 1 minus r. And again, that's only true if our r value is in between -1 and 1. Okay, so we're going to flip the script just a little bit, and we're going to start talking about power series. And a power series is really just a geometric series, except what we're going to do, for the most part, we're going to let a equal to 1, and r is going to equal to x. So if we do a replacement here, I'm going to get 1 plus x squared plus x cubed plus dot 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 x to the n. And we know what that sum is. It's equal to a, which is 1, over 1 minus r, which is x. And so in geometric, we would talk about this being the sum, because it's typically a number, because a and r are numbers. And here, we were talked about this as being a function, because then x is some function of x and this. And so we're going to flip it and say, well, instead of saying that this infinite series is equal to this function, we're going to start with the function. And we know that that function can be approximated by this polynomial. And the beauty of all of this is that we take a complicated function and we can write it as a polynomial. Now, it is an infinite polynomial, but in most cases, we don't really need all the terms to give us a good estimate for what this value is at certain x values. Okay, so this is what they would call the power series. And we also know that this pattern exists. Because once we know this pattern, then we can do all sorts of other patterns. We can do a replacement. We can do 1 over 1 plus x. And all I'm doing here is putting a negative x in for this x, because then it'd be 1 over 1 minus x, which is what this is. If you put a minus x in for x, it's going to still be a 1. It's going to be a minus x. But minus x squared is still plus x squared. Minus x cubed is going to be minus x cubed, and so on. And so you just get the alternating version of x to the n. Super similar. One's the alternating geometric series, and one is this. But I can do this for anything I want. I can do this for 1 over 1 plus x squared. That's this exact same series, except I'm putting an x squared in for x. So it's still going to alternate, except it's going to go second, fourth, sixth, because I'm putting in an x squared for an x. It's still going to alternate, so it's -1 to the n, and it's x squared to the n, which is x to the 2n. Okay? And so these two are just built from this. We can build anything we want. We can make this 1 over 4 minus x cubed. That's just like this series, except a 4x cubed instead of an x. So it's 1 plus 4x cubed plus 4x cubed squared plus 4x cubed plus dot 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 dot, all the way into 4x cubed to the n. And again, we have a polynomial approximation for this function. One of the other things that we can do with these series is that we can take the integral of it. And so if I look at this series and I take the integral of both sides, the integral of the function would be the natural log. But if this integral equals the natural log, then the natural log must be able to be written as the integral of this polynomial. Integrating this polynomial, all you're doing is doing the power rule. Increase the power by 1, divide by the new power. So integrating 1 gives you x. Integrating negative x gives you negative x squared over 2. Integrating x squared gives you x cubed over 3. Integrating that gives you minus x to the 4th over 4, plus dot dot dot. And then integrating the general term. It's still going to alternate. And the general term, instead of x to the n, it's going to be x to the n plus 1 over n plus 1. I just integrated everything. And so now we have a polynomial approximation for the natural log. I can do this one and integrate, and I can get inverse tangent. And again, I'm going to take inverse tangent, which we'll call a crazy trig function, and I can write it as a polynomial. Polynomials have Really easy. Derivatives, integrals, x-intercepts, y-intercepts. You can find their changes in concavity really easy. You can find their maxes and mins really easy. Polynomials are nice. Logarithms, inverse tangents, they have odd things that aren't as easy to analyze. Even something like this. This rational expression has crazy vertical asymptotes, crazy maxes and mins, where it's going to be very, very, very similar to the polynomial. So going back to inverse tangent, the integral of this is inverse tangent, and so we just integrate this, and we get x minus x cubed over 3 plus x to the 5th over 5, and so on, plus dot, dot, dot. It's the alternating series, and all we have to do is integrate this, x to the 2n plus 1 divided by 2n plus 1. And so we have all of these patterns, okay? These are the 4 big ones, this one, the alternating version of that, the natural log, which is the integral of this, and then we did this one just so we could look at the integral. And so that we have those 4, and those 4 are the start, okay? There are other patterns that we know and then can use. And so what we need to decide is the pattern for like sines and cosines. So we talked about this in class, and we'll build it in another video. But sine x is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot, dot, dot. And so it's an alternating series that goes up by odd powers divided by the exact same corresponding factorial. And then if I can do this, then I can do anything. I can do sine of 5x, because I'm just taking a 5x and replacing it with x. So instead of x, I write 5x. Instead of x cubed, I write 5x cubed. And so on. I'm just doing a substitution. And that's the beauty of the patterns, because I don't have to memorize anything else. A sine curve is a sine curve. So 5x to the 2n plus 1 over 2n plus 1 factorial. It's just a simple substitution. Okay? I can even do things like x squared times sine of 2x. Well, this is just x squared times sine of 2x. Well, sine of 2x is just putting a 2x in here. 2x minus 2x cubed over 3 factorial plus 2x cubed to the 5th over 5 factorial plus dot, dot, dot. And then I can put that x squared in and say this is then 2x cubed. Let's distribute this. So this is going to be 8x cubed over 6. So 8 over 6 is 4 thirds, and that's x cubed, so that's x to the 5th. And then after this is going to get a little complicated, because this is going to be 2 to the 5th is 32, 32 over 5 factorials, 32 over 120, and that's x to the 5th, and then another one, x to the 7th plus, and you can keep going. And so I've taken this ridiculously complicated function, which is a squared times a sine, and I've wrote it as a polynomial. Again, I don't have to approximate a polynomial, it already is. What it is, I can just distribute it into the end. So we did sine, we can do cosine. Hopefully it makes sense when you think about the fact that sine is a nice odd function. And so look, it's the summation of a bunch of odd polynomials. Cosine is an even function, and so it should be the evens. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot, 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 dot. That's an alternating x to the 2n, all the even powers, divided by the corresponding factorial. And then again, we can do all the substitutions we want. We can do cosine of x squared, we can do cosine of 5x, we can do whatever we want. And again, sine and cosine are 2 additional ones that we need to know. And then the last pattern is e to the x. E to the x ends up being 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. And it's not an alternating one. It's just x to the n over n factorial. And it's important to start thinking of these general terms as things we can look at. Again, so the seven values, let's see if we can put them all in here at once, is sine, cosine. Oops, I don't think that's probably going to work very well, but we have sine, cosine, e to the x, And then we have the other ones that were on the other page. 1 over 1 minus x, 1 over 1 plus x, the natural log of 1 plus x, and tangent inverse of x. These 7 are what they call the MaClaurin series, and they're just the patterns. They're not anything specific, but we didn't build them from scratch. And if you know these 7 patterns, then you can do a whole bunch of other substitutions.